Hello. Today, we're going to be analyzing lines of fit. And the first thing that we need to talk about when we're analyzing lines of fit is a residual. So basically, a residual is the difference between our actual data point and the point on our line of fit for a certain x value. So you take for every data point, you just do the y value of the data point minus the y value of the line. So that gives us the difference between the actual data point and then the line, which is our prediction or our line of fit that we're trying to say represents all of the points at once. So if a point is above the line of fit, then it will have a positive residual because we're doing the y value of the point minus the y value of the line. If the data point is below the line, it will have a negative residual because then we're taking a lower number and subtracting a number that's higher. So it's always the y value of the point minus the y value of the line. That's your residual. So if a point is above the line, it has a positive value for residual. And if a point is below the line, it has a negative value for residual. And the residual can be 0 if the point is right on the line. So what we can do is for a data set, we can take every one of these points after we get our line, take every data point and find this residual, and then we can plot the residuals. And we can look at the plot of residuals to determine whether it's a good linear fit, meaning like does this line really do a good job of predicting this data set? So here are some things that we can look for in the residual plot to tell if it fits a data set. So if the model is a good fit, then here's one thing. The absolute values of the residuals are relatively small. Meaning the distance, whether it's going up or down, the distance of the point away from the line is pretty small. We don't want really big residuals. The bigger the residual is, that's kind of the worse the line represents the data. And then the other thing to look for wait, what? This is not what I was trying to do. Okay, starting over. My little pen messes me up sometimes. So we are looking for small residuals, right? We want small residuals. And then we want the residual points to be more or less evenly dispersed. Oops, that's crossing it out. We want them evenly dispersed around the x-axis, right? Or the horizontal axis. If it's not a good fit, then the residual points will form some type of pattern. And that would suggest that the data are not linear, right? We can't use a linear model for these. If you get wildly scattered residual points usually means there might be no correlation with your data between the x and the y value. Okay, so let's look at a couple of examples where we look at the residuals and make a little residual plot and then interpret what that means about the line of fit. So in the last section, we did an example where we had the sales of I forget what it was, a movie or something, a DVD. After a certain number of weeks had gone by, and like the first week they did 19 million, the second week they sold 15 million, third week they sold 13 million, and so on. Now we we want to analyze, we found out that we found this line of fit back then. So what we want to do now is we want to try to decide, find out, analyze if that equation is a good fit. So here's what we'll do. We will start. So right now, this is our, these are our data points, right? So these are our actual Y values. Our predictions are going to be, and then sometimes when we do this later on in statistics, you'll say when we do a prediction, they'll do a little hat. They'll do a little hat, a little kind of like hat like that. They'll call it Y hat. And you'll see residuals written as Y minus Y hat sometimes. So Y is the actual data point, and then the one with the hat is the prediction, is the one we get from our formula. So what we're going to do is I'll say, all right, right here, we'll figure out what's the predicted Y value. So our actual Y values are the data point Y values, and our predicted Y values are the ones we get from plugging X into our equation. Oh, I hope my mute button worked. I just did a big sneeze. Okay, so when X is 1, we're going to do Y equals -2 times 1 plus 20. -2 times 1, that's just -2. So Y would be -2 plus 20 is 18. So our predicted Y value when X is 1 would be 18. Then we'll just do it for each different X value. So what about when X is 2? So then we're doing -2 times 2 plus 20. -2 times 2 is -4. -4 plus 20 is 16. So this one would be 8. And you'll start to see a pattern develop here. When X is 3, -2 times 3 is -6. -6 plus 20, or 20 minus 6 is 14. You can see the pattern is going down by 2 each time X goes up by 1. And that's really your slope, right? Your slope right here tells you that the Y value goes down by 2 every time X goes up by 1. So we can complete the pattern pretty easily just by factoring for 2 to get each successive Y value. So there's our predicted Y values. Then what we're going to do is we're going to get the residuals for each one. Okay, so erase the little scratch work I did over here. I'll show you on the next problem how we can use the Desmos calculator to make those calculations really easy, especially when we have a more complicated equation to work with. Okay, so now we're going to do the residual values. So this is the actual Y value minus the predicted Y value. So actual minus predicted. So 19 minus 18 is 1. Our first residual is 1. And what we can do is I'll show you how we're gonna plot these. Here's my x-axis. 1, 2, 3, and I just need 1 through 8. 4, 5, 6, 7, 8. And our when x was 1, our residual was 1. So I'll put a dot 1 unit up. I'll make a y-axis too. Okay, so we've got a residual of 1 for the first one, and my dot disappeared, so I'll make it again. Okay, when x was 2, we go, our residual is 15 minus 16. 15 minus 16 is negative 1. So when x was 2, our residual was negative 1. When x is 3, we're doing 13 minus 14, which is negative 1. When x is 4, we're doing 11 minus 12. That's negative 1. So the residual when x is 4 is negative 1. When x is 5, we're doing 10 minus 10, 0. So when x is 5, we have a 0 residual. When x is 6, 8 minus 8 is 0. So we have when x is 6, we have another 0 residual. Want to just let me draw a little circle. 7. When x is 7, we're doing 7 minus 6. Our residual is 1. And when x is 8, we're doing 5 minus 4, which is 1. Now, what we're looking for is to see if they're sort of evenly dispersed around the horizontal axis. So we've got 3 above and 3 below, and we've got 2 right on it. So that looks pretty good. We don't have like they're not super scattered all crazy, which would indicate wildly scattered residual points suggest that the data might have no correlation. We don't have that. If the model's not a good fit, they will form some type of pattern. Usually it's like a U-shaped pattern that we look for to indicate it's not linear. But look at this. Our residuals are relatively small, 1 or negative 1 or 0. And the residual points are more or less evenly dispersed about the horizontal axis. So all of our residuals are pretty small, 1 or negative 1 or 0. And they're dispersed somewhat evenly around the x-axis, like on top and bottom. So we will conclude that, yes, this is a good fit. All right. So let's take a look at another example real quick. This table shows the ages and salaries. So ages is the X value, salaries is the Y value in thousands of dollars, so 42,000, 44,000, and so on. Of 8 employees, these are the 8 employees at a company. The equation y equals 0.2x plus 38 models the data. Is the data a good fit? All right, so what we need to do is for each input value, figure out the predicted y value. So y equals 0.2x plus 38. So when x is, this is one where I probably want to use a calculator. And so here's what I'll show. I'm going to show you a little tricky poo. I'm going to go to sonos.com/calculator. I will post link in the chat. And here's what I'm going to put in here. My equation is y equals 0.2x plus 38. So what I'm going to do is I'm going to write it in function notation. I'm going to say f of x equals 0.2x plus 38. And you can see it was trying to graph it down there. And once I put plus 38, it moves the y-intercept way up there. Now, what's cool is we can just do this now. F, little f, of 35. And it'll tell us the answer is 45. So let's look back here. So when x was 35, the predicted y value was 45. I'm going to put a little 45 down there. Then next is 37. So then I can just go and change this to 37. And it's 45.4. Then 41 is the next value. And the y value we get is 46.2. And then 43. F of 43 is 46.6. Then 45. F of 45 is 47. Then 47. F of 47 is 47.4. Then 53. F of 53 is 48.6. And 55 is last. F of 55 is 49. So now we're going to come through and we'll do our subtraction. We're going to subtract 42 minus 45. So that would be -3. And let's see, we're going to need to make a plot here. So we're going from 35 to 55. So 35 is the lowest, 55 is the highest. Halfway in between them would be 45. That would be 40. That would be about 50. Okay. And then we'll need all that one, this -1, and then that's how we go. So when x was 35, our residual was -3. So I'm going to have to change my y-axis here so I can get a -3 on there. Better if this was straight, huh? I'll try. -1, -2, -3. 1, 2, 3, 4. Okay, now our first residual at 35 was -3. Okay, stop. I need to make it stop doing that. I just want to make a dot there. Okay, now next, 44 minus 45.4. A little cat, what the heck? Calculator button. 44 minus 45.4, -1.4. So let's see, that's at about 37. So maybe right around here. And that's -1.4, so maybe around there. Okay, for this one, 47 minus 46.2, that would be 0.8. And when x is 41, the y value is 0.8. When x is 43, we're doing the residual is 50 minus 46.6. So that's going to be 3.4. So that was when x was 43, which is about here. And then the y, 3.4. So up here a little bit. Then when x is 45, we're doing 52 minus 47, which is 5. So 5 would be up here. 45 and 5. Then when x is 47, the residual is 40 or 51 minus 47.4. That's going to be 3.6. So when x was 47, the residual is about 3.6. Then when x is 53, the residual is 49 minus 48.6. That's 0.4. So 53 would be about here, and 0.4 would be like this. And then the last one, 55, we're doing 45 minus 49, which would be -4. So at 55, our residual is -4. So now looking at our residual plot here. For one thing, it has sort of like this curve shape to it. It starts low, it goes up high, then it turns around and comes back low. So it has this upside down U shape kind of a look to it. And that's not really what we want. Remember, we're looking at we want them to be evenly dispersed. And if it says if there's some type of pattern that would suggest the data are not linear. And also for it to be a good, the linear model to be a good fit, our residuals would be relatively small. And so you want your residuals to be kind of small and close around the x-axis. And you don't want to see a pattern. And what we have is we have residuals that are far away from the x-axis, and we have a pattern showing that. So what that tells us is that this model is not a good fit. And this data probably is not linear, meaning that the older you get, you don't keep making the same, like every year you get older, you're not going to get the same amount of arrays. Like sometime around when you're 45 is when you're going to be getting your biggest raises. And then as you get older, you're not going to get as many raises, is what it kind of seems like. Okay, so no, that was not a good fit for the reasons we discussed. We have a pattern, they're not very close to the x-axis. Okay, so now we're going to, we talked a lot about residuals. And then we recently started learning how to use a calculator to do linear regression to find a very precise line of best fit. And this is always the best model for the set of data. And what it does is it goes through and it tries to figure out which line would give you the smallest residuals. And a calculator can do that for us pretty quickly. It's a super long thing to do by hand. And a calculator will give us a value R called a correlation coefficient. And there's two values that they give us on the calculator. They give us R and they give us, they give us R squared also. We'll talk about R squared later. But R is the correlation coefficient. So R can be positive or negative. R squared can only be positive, right? Because when you square something, it's always positive. So the correlation coefficient can be positive or negative, and it goes from -1 to 1. The closer to -1 or 1, the better the model is. The closer to 0, the worse the model is. So when R is close to 1 or -1, there's a strong correlation between the variables. And as this R correlation coefficient gets closer to 0, the correlation is weaker. So this is like R equals 1 is a strong positive correlation where the line really matches it, but it has a positive slope. Here, there's no correlation when R is 0. And then here's a negative correlation, meaning it's a really strong correlation, but it has a negative slope. So at the ends, the 1 and the -1, those are the strong correlations, either a negative correlation or a positive correlation. And then in the middle is no correlation when R is 0. So let's use our Desmos calculator to find the line of best fit for this. So this table shows the duration, X, in minutes of several eruptions of the Geyser Old Faithful. So this is like how long it was erupting, how many minutes did it erupt for. And then the Y value is the time in minutes until the next eruption. So we're going to use a graphing calculator to find the equation of best fit. Then we're going to plot the data and graph the equation in the same viewing window. And what we're going to do is we're also going to look at the residuals. So what I want to do, we're going to put this data in our calculator. So I am going to need to come over, not that calculator, this calculator. Okay, so what we're going to do now is we're going to add table. And in the X1 column, we're going to put all of our X values. So 2.0, 3.0, you can do them, you can go down and make all the X values, or you can make them one pair at a time. And when you're, I don't know, like you want to make sure that you're getting the X and Y pairs together. So maybe I'll put those in together. So X was 2, Y was 60. So when X1 is 2, Y1 is 60. When x is 3.7, y is 83. 3.7, 80. And 4.2 and 84. 4.2, 84. And 1.9 and 58. 1.9. And 3.1 and 72. Point 5 and 62. And 4.4 and 85. And 3.9 and 85. Okay, now I'm gonna change the axes here. My x-axis, I don't need it to go to like -70 and all the way to +200. My x values were like from like 1 to 4, 1 to 5-ish. So I'm gonna do this. I'm gonna say 1, 2, 5. And then my y-axis is actually pretty good. I don't need to change my y-axis very much. Now what we're going to do is we are going to tell Desmos to do linear regression. So we're going to say y1 equal mx1 plus b. And so you can see they give us our slope is 11.99. Our y-intercept is 35.1068. And our R value is 0.9798. So let's transfer that information back over to our slideshow. So we got m equals 11.99. B was 35 point, I'm going to round it to 2 decimal places, so 35.11. And our correlation coefficient R was 0.98. Okay, so we did part A. Identify and interpret the correlation coefficient. So the correlation coefficient is 0.98. And what does that mean? That means that the model y equals 11.99x plus 35.11 is a good fit. A strong, positive correlation. And then interpret the slope and y-intercept. Well, first I want to come back over. We can interpret the slope and y-intercept. The slope says, let's see, what is the rise over run? So the time, the slope means that, so rise over run. So the time goes up by almost 12 minutes every time the eruption duration increases by 1 minute. So say if you went from a 2-minute eruption to a 3-minute eruption, the time should go up by about 12. And that kind of makes, because when we go from 2 to 3.1, that's going up by about 1 minute. And our duration, our time in between went up by about 12. And then what does the y-intercept mean? Well, that means if no time has gone by, or if the eruption lasts 0 minutes, then it should be about 35 minutes until the next eruption. So if you get an eruption that just goes for 1 second, then it should be about 35 minutes until the next eruption. But I also want to show you how to show the residual plot. And all you have to do is see where it says residuals E1. The little E stands for error. It's kind of like how far off are we? So if we plot our residuals, it'll show if you just click on plot, first thing it does is it calculates all your residuals up here for you. And then it plots them down here so you can get a visual look and say, look, these are really close to the x-axis. The majority of our residuals are pretty small, and they seem to be kind of like evenly dispersed around the axis. We don't see like a specific pattern. If you see like a big U-shaped pattern, then you should be worried. Or if it's a big U-shaped pattern like this, then you should be worried. Or even if you get like a line that's going, like if your residuals are lined up in a line, that's probably not a good indicator either, unless that line is the x-axis. Okay, so these problems are a lot easier when we have a calculator doing most of the work for us. What's next? All right, so now using a graph or equation to approximate a value between two known values is called interpolation. Using a graph or its equation to predict a value outside the range of known values is called extrapolation. And in general, the farther removed a value is from the known values, or the further away you're extrapolating, the less confidence you have in the accuracy of the prediction. So let me give you an idea of what that means. So interpolation would mean if we were going to say, well, let's say when x is 2.7 or 2.8, right? If you're going to say, well, predict how long the wait will be when the geyser erupts for 2.8 minutes. Well, that's in between our known data points, right? That's in our normal domain. So that would be interpolation, because we're predicting a value that is within our set of values. It's inside our set of values. So that's interpolation. If we were asked to predict how long would it be in between the eruptions when it erupts for 6 minutes, well, that would be extrapolation, because that's outside of our data set, right? So it's outside of there. So extrapolation means when you're predicting things that are outside of where all your data points, and interpolation is when you're predicting for a value that's inside with your data points. And the further away you get from your data points, right? If we're trying to make predictions for when it's a 10-minute eruption, that might not be as reliable as if we are predicting for a 3.3-minute eruption. That would be interpolation. So the further away you're extrapolating, the less reliable, in general, your prediction will be. Okay, so now we're going to refer to example 3, and we already have it. We already have our graph over here, so we're good. Use the equation of the line of best fit. So we're going to use the equation to approximate the duration before a time of 77 minutes. So our equation was 11.99. We might as well just make it 12 and 35, just to make the math easier. So we're going to say y equals 12x plus 35 is our equation. So we got Our equation was y equals 12x plus 35, right? It was really 11.99 and 35.1, but we're going to kind of round to whole numbers just for this. Approximate the duration before a time of 77 minutes. So duration, if we look back at our duration was the x value, and then the time in between was our y value. So what they're asking for is they want us to solve for when y is 77. So they're asking us when there's a time, if there's a gap between eruptions of 77 minutes, then how long was the eruption right before that? So what we're going to do is we're going to plug 77 in for y. And then solve for x. So to solve for x, we need to subtract 35 from both sides. $77 minus 35. $42. And to get x by itself, we would divide by 12. So then we're doing 42 divided by 12, 3.5. So the duration of the eruption before a 77-minute gap would be 3.5 minutes. And then part B is to predict the time, the delay time after an eruption that lasts 5 minutes. So that's the x value. So y equals 12x plus 35. We're going to plug a 5 in for x. Twelve times 5 is 60. So it would be about a 95-minute gap after a 5-minute eruption. And now, like the last one is to talk about correlation and causation. So we've talked about correlation so far. Two things can be correlated. Just mathematically, you can do the, you can put it in the calculator, get an R value, and tell if there's a strong correlation or not. But that doesn't determine whether or not it's causation. Causation is more of a thing that you have to kind of process mentally. When a change in one variable causes the change in another variable, it's called causation. Causation produces a strong correlation between two variables, but the converse is not true. That means that a strong correlation does not imply causation. So that sounds like a lot of vocabulary right now and a tongue twister maybe, but looking at an example might help us understand it better. The difference between correlation and causation, because both of these situations have a strong correlation, but not both of them have causation. Okay, so this says causal, not casual. So tell whether the correlation is likely. If so, tell whether there's a causal relationship. So first of all, is correlation likely? That's the first question. And then, is there causation? So are these correlated? So the time spent exercising, so that would be like your input, and the number of calories burned, output. Are X and Y related? Are they correlated? Does the more time you spend exercising have an effect on the number of calories you burn? That sounds like a positive correlation to me. It sounds like the more I exercise, the more calories I'm going to burn. So that has these ones are correlated, so they have a correlation. And then does the amount of time you spend exercising actually cause the number of your calories burning to increase? Yeah, exercising actually does cause that. So they have correlation and causation. But look at B, the number of banks in a city and the population of a city. So if a city has a lot of banks, it seems like it would be correlated that that city would have a lot of people in it, right? If a city has a lot of banks, then it probably has a lot of people. So they're correlated. And there's probably a good, strong, positive correlation between them. Cities that have lots of banks probably have lots of people. But the question is, does the number of banks cause the population to change? If you put more banks in a city, will that make the population grow? Is the number of banks in a city causing the population of that city to be large? Not necessarily, right? So we would say this has correlation, but not causation. What happens a lot of times is people on the news or whatever will say, look, the data shows blah 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 blah. It might be a correlation, but not a causation. It might be something that oh, maybe it's the other way around. Maybe the population of a city makes you have more banks. Maybe if the city is more populous, then you could have more banks. There might be causation in that direction, but not in this direction. The number of banks in a city doesn't determine how many people live there. You put more banks, that's not going to mean more people live there. Okay, so that is the end of the lesson. Let me stop the recording and I will go over the assignment with you.